Hi everyone. In this video we will talk about a spring and a mass under gravity. So the left hand side panel I have the arrangement that we're going to consider today. This shows you an unstretched spring. The spring is not subject to any external force, and so it is at its natural length. And in this second part of the figure, I've now attached a block of mass m to the bottom of the spring so that the block is hanging from the spring. Now as soon as I let it go, gravity is going to pull down on the block, so the block's going to start falling, which will cause an extension in the spring. And when there's an extension or a compression in the spring applies a spring force. Because of the extension, the spring is going to start pulling upward on the block. So at some point the block's going to stop and then start moving back upward. So via that, the block's going to oscillate back and forth, up and down essentially. So let's look at what happens when we start this system. So I let go of the block, and so it's going to first move downward and then back up, and it's going to keep doing that, and eventually it's going to come to an equilibrium. And the equilibrium position for the block will not be the same as that for the unstretched spring. That's because there is a force of gravity that's pulling down on the block. So in the equilibrium condition, the force of gravity must balance the spring force that is acting on the block, and these two have to be in opposite directions and have to be equal to each other in order for the block to come to equilibrium. So now we want to analyze this from the point of view of forces. So what I'm going to do is I'm going to look at this figure on my right hand panel. So this length is the unstretched length of the spring, and we are going to consider the downward direction as the positive direction. So y of t, that is shown over here, is represents both the position of the block at some time t, as well as it's the same as the amount of stretching of the spring at that instant of time t. So considering this arbitrary time t, let's now draw a free body diagram for the block. So for the free body diagram, we will have to put a downward force, mass times acceleration due to gravity. That's the downward force on the block, and in the upward direction the spring is applying a force, and that will be equal to k times y of t. Note that this force is negative, but I'm not explicitly writing the negative sign because I know that my upward direction is the negative direction. And under these two forces, the block is moving, it's also accelerating, and that acceleration, will consider that acceleration to be downward. And now we can apply Newton's second law. So Newton's second law will tell us that mass times acceleration is equal to the net force acting on the block, but the net force is equal to mg minus k times y of t. Okay, but remember, acceleration is the time derivative of velocity, and that's equal to double time derivative of displacement. So now we can plug this into our equation to write m times d2y dt2 is equal to mg minus ky, and this is the equation of motion of the spring mass system. Notice that this equation of motion is slightly different. We can actually reorganize and rewrite this differential equation in a slightly different manner. So I'm going to divide both sides by m and rearrange some of the terms to write this as d2y dt2 plus k over m y is equal to g. Alright, so this is another way of writing the equation of motion. SHM, this is sort of driven by gravity. Gravity is the external force, And so you notice that this differential equation is slightly different from what we had for our spring plus mass on horizontal frictionless surface. So if we go back to our horizontal frictionless surface part and look at the force equation, you notice that this was our equation of motion. It was an x was the independent, x was the dependent variable, t was the independent variable. But the right hand side of this equation had a 0, so the right hand side is 0. So but in this equation, y is the dependent variable, t is the independent variable, and g is on the right hand side is not 0. So right hand side is not 0. Okay, so this is slightly different. How are we going to solve this differential equation? Remember, our main goal is to find y as a function of t. That's the goal. So if we want to find y as a function of t, we have to solve this equation. And let's start by doing what we did last time. We said the displacement can be written as some constant times a sine of omega t plus delta. Okay, if we do that and then we calculate d2y dt2, since we have calculated this before, I'm going to skip and just write down what d2y dt2 is. That will be negative a times omega squared sine omega t plus delta. Okay, if we try to plug this into our these two into our original equation, then we will end up with a left-hand side is equal to 0 if omega squared is equal to k over m. Alright, since we need our left-hand side to be non-zero, our older prescription of writing y of t equals a sine omega t plus delta is not working anymore. What we can do is simply modify this a little bit. So we're going to write y of t is equal to some constant, let's call it c, plus a sine omega t plus delta. Okay, and then we can take 2 times the time derivative of y. Now remember, c is a constant, so it doesn't change with time. Because c is a constant, it's not going to contribute to the time derivative of y, so we will get the same time derivative. So we get negative a omega squared sine omega t plus delta. Great. Okay, now if we plug this in to our original equation, then what we get looks like negative a omega squared sine omega t plus delta plus k over m, and now we have to plug in the full thing y, which is c plus a sine omega t plus delta is equal to g. Okay, alright, now I can rearrange this, and what I'm gonna do is I'm gonna factor out the a sine omega t wherever I can. So I get a sine omega t plus delta multiplied by negative omega squared, and then a sine omega t plus delta also appears over here, and that appears with a k over m. So we get a plus k over m. Okay, and the other terms that are left over is k over m times c is equal to g. Alright, so one way of solving this equation then is to say that this is equal to 0 and that this portion equals to that portion. So we get omega squared is equal to k over m, and k over m c is equal to g, or c is equal to mg over k. Alright, so let's plug in this back into our original assumption for y. So that gives us y as a function of t is equal to mg over k plus a sine omega t plus delta. Okay, we can go further. What we could do is we could, just like in the earlier video, we had determined what y of t was at t equals 0. So at t equals 0, we know that we had let go of the block when y of t was 0. So that's the position at t equals 0. So y0 is equal to 0. Okay? Remember, y is always being measured from this level. Okay, from the level where the spring is unstretched. So at t equals 0, y of 0 is 0, which means that we should have mg over k plus a sine. Now t is 0, so this omega times t is also 0. We will get a sine delta, which means a sine delta is equal to negative mg over k. So that's one condition. And another condition that we can arrive at is at the initial instant I also let the block just go on its own. So I started it off with velocity v at time t equals 0 equals 0. So at t equals 0 we have dy dt, which is the velocity. Dy dt at time t equals 0 is also 0. So if I take the time derivative of y of t, the first term, which is a constant, this constant term will not appear, so we will only have a omega cosine omega t plus delta, and we have to evaluate that at time t equals 0. And this must also be equal to 0 because at the initial instant dy dt is 0. So this gives me a omega cosine delta is equal to 0. Okay, how is this possible? Well, a can't be 0. Omega is the frequency of oscillation. That's definitely not 0. Cosine delta must then be 0. So if cosine delta is 0, we know that delta has to be plus or minus pi over 2, 3 pi over 2, etc. We're just going to stick to the plus pi over 2 value. So delta equals pi over 2. So then plugging this in, we find finally that y of t is equal to mg over k plus a sine omega t plus pi over 2. Great. In addition, we also have a sine delta is equal to negative mg over 2. But what is delta? Delta is pi over 2. And sine of delta is equal to 1. So if I put that in there, then I get a equals negative mg over k. Okay, so now I can even plug this into my equation for y. So we get y of t is equal to mg over k minus mg over k sine omega t plus pi over 2. Alright, so this gives me mg over k times 1 minus sine omega t plus pi over 2. And so this is my solution to the differential equation. Once we have found the position of the block as a function of time, which is given by this y of t, we can go ahead and find its velocity and acceleration as a function of time. So what we can do is we can take y of t and take a single time derivative. So dy dt equals the velocity of the block as a function of time. And so if I take a single time derivative, I get negative mg over k times omega cosine omega t plus pi over 2. If I take two time derivatives, that will give me d2y dt2, which is the acceleration of the block. So that ends up being mg over k times omega squared sine omega t plus pi over 2. But then we notice that omega squared is equal to k over m, which means that m over k times omega squared, this quantity is equal to 1. And this quantity appears over here in the coefficient. So we can just replace that. We can just take m over k times omega squared and set that equal to 1. So that would give me that the acceleration is equal to g times sine omega t plus pi over 2. So that's the acceleration of the block as a function of time. Alright, now once we have found the position, velocity, and acceleration as functions of time, we can just simply plot them. And that's what I've done over here. T is the independent variable which has been plotted in all of these three plots along the x-axis, and along the y-axis is the position as a function of time, velocity as a function of time, and acceleration as a function of time. You can see that the block's position starts from 0 it increases. It's increasing because the downward direction, remember in our figures earlier, the downward direction was positive, so that's how the block is going. The block is moving downward, and it reaches some maximum maximum value of y, and then starts coming back downward. On the other hand, our velocity starts from 0. That's how we started the block off, reaches a maximum and then comes back down to 0, and it keeps oscillating back and forth like that. And the acceleration started off as being just a free fall, so 9.8 meter per second squared, right over here at time t equals 0. And then because of the spring, the acceleration, the magnitude of the acceleration goes down until it reaches a maximum value, again a maximum negative value, which means at this point the block is accelerating upward, and then it keeps oscillating like that. So that is our spring plus mass system under gravity. So finally, let's summarize what we have learned so far. Here we will summarize the driven oscillation part, where we have a hanging mass from a spring. So again, the things that we can talk about are y as a function of time. We found that this is equal to mg over k times 1 minus sine omega t plus pi over 2. So this gives us information about what happened at t equals 0. At time t equals 0, sine of pi over 2 is 1, so we have y of t is equal to 0. Y of t at t equals 0 is 0. And then we can find the velocity as a function of time, so that's equal to negative mg over k times omega cosine omega t plus pi over 2. And at time t equals 0, cosine of pi over 2 is 0, so that ends up giving us v of t at time t equals 0 is also 0. Acceleration as a function of time, we found that that is equal to g times sine omega t plus pi over 2. So that tells us that at time t equals 0, this acceleration is a function of t. At time t equals 0 is just acceleration due to gravity. Okay. The other things that we need to know are omega is equal to still square root of k over m. This is the angular frequency for the SHM. And we can find the time period, which is equal to 2 pi over omega, which is the same as 2 pi square root of m over k. This is the time period of SHM. Great. What about the frequency? Frequency is equal to 1 over omega. So that's equal to square root of m over k. That's the frequency. In this particular case, the amplitude of oscillations was, amplitude in our particular system was mg over k. Amplitude A equals mg over k. And note that when, after a long time, when this the sine part of this y as a function of t becomes 0, we will find that y at t goes to infinity, very long time later, is equal to mg over k. That's our equilibrium position. Alright, so that's pretty much the summary for our hanging mass from a spring. I hope you enjoyed this video. Thanks again.